In the previous video, we introduced the formula for the sum of the terms in a geometric series. Now that we're able to use the formula, let's see where it comes from. We're going to use a similar approach as we did in the previous video on arithmetic series to figure that out. So here, we're going to start with a specific example as we did previously, and then replace these with letters, variables, in order to work out a general formula. If we wanted to find out the sum of this geometric series, 3 plus 12 plus 48, etc., we could start by writing it out. If it goes up to 3 times 4 to the 9, the number before that would be 3 times 4 to the 8, because the common ratio is 4, the number before that would be 3 times 4 to the 7, etc. What we did in the example before with arithmetic series is we then wrote this backwards underneath, and that's not going to work exactly for working out the sum of a geometric series, but we're going to use a similar approach. First of all, let's recognize that if we could add all of this up, that would be what we're looking for, S sub n, the sum of this series. Instead of doing that, though, let's apply this trick. And this is not necessarily something you might spot, but once you've seen it, you'll see how it all works out quite nicely. If I multiply the whole thing by 4, every term in this series by 4, I'm going to multiply 3 by 4, and I'm going to get 12. I multiply 12 by 4, and I'm going to get 48. If I multiply 3 times 4 to the 8 by 4, I get 3 times 4 to the 9. And if I multiply 3 times 4 to the 9 by 4, I get 3 times 4 to the 10. And that's because I've multiplied by the common ratio, it's shifted everything up one place. So if I've multiplied this whole row by 4, then instead of having S sub n now, I actually have 4 S sub n on this bottom row. And now, if I draw a line underneath, in the previous example we had columns, we're going to treat it like columns as well here. Notice that these are the same. There's some unpaired things. This 3 times 4 to the 10 over here and this 3 are unpaired, but everything else is paired. So if I do the bottom row, 4s sub n minus the top row, s sub n, so I'm taking the bottom row and subtracting the top, then this is going to cancel, this is going to cancel, that's going to cancel, that's going to cancel. What's not going to cancel is this, and because this is what I'm subtracting from, this is going to remain 3 times 4 to the 10. And I've subtracted the top row, everything's canceled except for that 3, so I have that. If that was confusing, you might want to pause, rewind, and go back over that. The idea is I've multiplied the top row by 4, it's shifted everything over 1, it's created a kind of offset pairing where I've got this edge hanging out and this edge hanging out here, unpaired. Everything else is paired, and I subtract the top from the bottom, so 4s sub n minus s sub n. This is uncancelled and this is uncancelled. On the left side then I have 3s sub n, and on the right hand side I have a common factor of 3 which I can factor out, giving me 4 to the power of 10 minus 1. Now what I wanted was the sum of this row. The sum of this row is s sub n. Right now I have 3s sub n, so I want to divide this side by 3. There's a nice common factor of 3 on this side as well, and I can divide that out there. So s sub n is equal to 4 to the power of 10 minus 1. And that's going to be a very big number. We're just going to leave it like that. But the point of this was to illustrate how multiplying by the common ratio shifts everything over one step and allows you to do this fancy canceling out by subtracting the top row from the bottom row. Now let's use that same trick to derive a general formula for the sum of the terms in a geometric series. So imagine we had a geometric series with first term a and common ratio r. The first term would be a, the second term would be ar, the third term would be ar squared because we multiply by r each time. Remember that the general term is ar to the n minus 1, so the last term is going to be ar to the n minus 1. The term before that would be a times r to the n minus 2, etc. And in between, let's just put dot, dot, dot. This is the sum that we want. Remember that in the previous example, we then multiplied by the common ratio. So if you multiply by r, so if we're going to multiply by r, then a multiplied by r gives me ar. Ar multiplied by r shifts over and gives me ar squared. And everything does in the same way. Ar to the n minus 2 multiplied by r gives me AR to the n minus 1, but this one multiplied by r gives me AR to the n by the power rule of exponents, or rather by the by exponent rules, AR to the n minus 1 times r gives me AR to the n. I've multiplied everything by r, so this row is r times s sub n. Again, that's generated columns that are paired. But there's one unpaired thing here, and there's one unpaired thing here. The next thing that we did in the previous example was we subtracted the top row from the bottom row. So we did r s sub n minus s sub n. Everything here in the middle canceled. This did not cancel, AR to the n, nor did that, minus A. Then we can do some common factoring. We have S sub n as a common factor here, so S sub n times r minus 1. When we common factor that out, and here we have a common factor of A, so we get A times r to the n minus 1. Remember, what we're trying to get is a formula for S sub n on its own. So dividing both sides by this r minus 1, we get A times r to the n minus 1 over r minus 1. And that's where our formula for the sum of the terms in a geometric series comes from.